So what are you, HDMI?
Yeah, it's just this laptop. I think you should connect to that, extend to that screen.
Okay, extend. Oh no, sorry, not to extend. You can do simple. Duplicate. Sorry, I chose the wrong one.
That's fine.
Okay. So for our next talk, we have Abhishodh Prakash. He's also from Oxford. He's going to tell us about multiversality and unnecessary criticality in one dimension. Looking forward to it.
Thank you. And both of these names are not inventions of mine. They're both by Senthil and P. So just bring it out there. Thank you for this opportunity to talk about some recent work I completed with Sid Parameswaran and Michele Fava at Oxford. It's titled Multiversality and Unnecessary Criticality in One Dimensions.
Oh, it's fun. Yeah, I like it.
So,
Go ahead.
Sorry. So these are novel beyond Landau quotes, critical phenomena in a reasonably tractable setting. What they mean is as follows: like multiversality refers to a phenomenon where there are multiple universality classes on a single critical surface separating two phases. And unnecessary criticality is a phenomenon where one has a stable critical surface not separating any two phases within a single phase. So I'm going to provide a generic setting, meaning this is not a fine-tuned phenomenon. It's stable to a class of small perturbations where such exotic critical phenomena are observed. So the way I would like to anchor the discussion, at least to myself, is as follows. So this is a garden variety phase diagram. The phases, a phase diagram has two ingredients broadly: the phases and phase transitions. Characterizing both of them is a complicated affair. Like one needs to characterize the phase, symmetry, order parameters, out-boundary modes, response to gauge fields, things of this kind. Phase transitions, on the other hand, are classified by universality classes and characterized by the values of critical exponents, scaling operators, central charge of the theory, and so on.
These phase transitions are continuous transitions.
Yes, I'm only going to be referring to continuous transitions. So two seemingly extremely simple questions are: what is the relationship between these two ingredients? Meaning, if I say I have a certain universality class, can I say anything about what phases it separates? On the other hand, if I give two phases and then guarantee that there exists a continuous transition between them, can I say what the universality class between them are? And what I hope to convince you is that the answers to both of these questions is largely unknown, and as the examples I'm going to provide. So let me begin with the first question, which is: if I'm given a critical theory with a certain belonging to a certain universality class, can I say what the phases are? For example, if I have the Ising universality class, which I denoted as I, can I say what the surrounding phases are? There's one obvious example, which is if I take the Ising model and drive it to criticality, we know what the phases are. There's the Ising symmetry that's unbroken and Ising symmetry that's spontaneously broken. But we also know that the Ising universality class appears in separating phases as a transition between phases, which have nothing to do with any global symmetries. For example, if I couple the toric code with the magnetic field and drive the magnetic field beyond to a certain critical value, the system undergoes a transition from the Z2 quantum spin liquid to a trivial paramagnet through the Ising universality class. On the other hand, Kitaev's Mariana chain, which separates a topological superconductor from an ordinary insulator, the transition also belongs to the Ising universality class.
Instances 2 and 3 dual to instance 1.
2 and 3 are in different dimensions, so I don't see how.
Well, okay, so but generally there's a it's a chain. Well, generally there could be duality transformation, which brings you either in one dimension or in two dimensions to the corresponding ether. I thought it's happening in cases 2 and 3. You can do a duality transformation.
Possible. Like you're saying, there's a way to argue that the phase transition in this model also happens to be a universality class, for which one uses dualities. But the fact remains that the phases are not characterized by symmetry being spontaneously broken. And that's the entire deal of
I think you would declare a local symmetry being spontaneously broken.
no, I mean any symmetry.
Because I would say there is a Z2 symmetry until I call it spontaneously.
No, I think one can prove that the toric code phase is stable to any perturbations, literally any local perturbations.
Is that the same
Is that the same
as there being null symmetry, even for non-local?
Yes, if I can explicitly break symmetry and the phase is stable, there's no symmetry being spontaneously broken.
Carry on. We're gonna have some good discussion.
Yeah,
sure.
I don't understand what is criticality here. I mean, if I measure the heat capacity, right, I would expect the exact same result for the ketide marijuana chain and for the transverse fielizing mode. If I measure, this is one critical exponent. Another critical exponent, eta, measures correlation functions of operators with local support. And there I can tell the difference between these two objects very well.
What two objects?
Oh, between a state that has an order parameter or a state that is a topological transition. So these are very, very different states from that perspective.
I agree with you.
What do you mean by criticality now? What is the object that we are supposed to look at to say these are the same, I can't tell the difference, or these are different phenomena?
I mean, that's a big question, but a limited answer perhaps is that there is a critical theory defined by conformal field theory, where there are scaling operators, anomalous dimensions, and so on. We could assign symmetry charges and then actually detect where this is coming from.
Yeah.
But if we consider the data to be scaling operators, critical exponents, and things of this kind, I would say they're the same.
Let's measure the spin correlation function of the ketide chain. I get the exact same result in the spin correlation function of the Ising model.
So I didn't get the question though. I agree with you. Yes.
I don't think so. You do get the result.
Sorry?
It's a very different objects. One is it's a non-local representation of the other object. So they should give me very, very different results. The spin correlation function of the ketide chain is non-interesting, and yet and one of the Ising model is clearly.
No, I think I'm not clear about what the question is, because indeed there are operators which have exponentially decaying correlation functions, and in one model, and there are certain operators which don't. But the critical theory is identified by what operator maps to what operator. For example, if I have one scaling operator that comes from the Ising model, then I can map it onto the scaling operator that comes from the ketide chain, then that's basically done.
I think we should let him go on. We'll have a good discussion afterwards.
Well, my point being, and we could discuss whether you agree with this, is the universality class does not tell us what the phases surrounding are. This was supposed to be an example for that.
I disagree.
Okay, that's even better. Okay. Well, you don't need to take this example. Our example should also work. So there's the converse question, which is, if I tell you the phases, can you tell what the universality class is? And here the answer was supposed to be, is considered to be more unambiguous, in the sense that if I have the Ising model and symmetry is spontaneously broken, I know we get the Ising universality class. That was the assumption generally. And of course, there are some caveats. For example, in this diagram, as long as I tune one parameter, there's a universality class. But if I tune multiple parameters, we all know that there are there's multi-criticality, and that could be a different universality class compared to the original one. So for example, IAB can be different from the center point, which is IABC. Although this is generally considered to be true, meaning that if I have two phases, the universality class of the phase transition separating is uniquely specified. If this is considered to be true, there's actually no fundamental reason for it to be true. And in fact, I'm going to provide counterexamples to this. The counterexamples that I'm going to be providing are as follows. These two phase diagrams are supposed to be counterexamples. The first one has two phases, which is a trivial paramagnet and a symmetry protected topological phase, where the critical theory has multiple universality classes. And I just labeled it by the central charge of the critical theory. And that changes without any change in the surrounding phases. A second one is a critical theory that's not even associated with any phase transitions because it's a finite critical surface that abruptly terminates lying within a single gap trivial phase. And the rest of the talk is going to be about models that actually give you these phase diagrams. Let me mention that this phenomenon was postulated to exist by Senthil and B in this paper, which was published in PRX in 2019. Their setting is a bit more complex. They consider 3+1 dimensional field theories with non-abelian gauge fields belonging to the group, symplectic group with NC colors and coupled to large number of fermions, which are transformed as a fundamental representation. They postulate that this field theory, which produces diagrams of this kind, emerges from some microscopic model. Our setting is relatively simpler. They're 1+1D spin ladders and or coupled Luttinger liquids, and many things that are not accessible in the original setting are also accessible, and it's also easy to verify them analytically and numerically. So let me begin with the first example. So the model is relatively simple. It consists of two copies of the XXZ chain with bond alternation, alternative bond strength. One important detail is that the ZZ coupling, the ZZ coupling is negative, which should be ferromagnetic coupling. This is an important requirement. And the vertical coupling, the rung coupling between the ladders is a simple ZZ coupling. I'm going to be charting phase diagrams by varying the vertical coupling JPerp and the strength of bond alternation. The phase diagrams are going to be two-dimensional, and these are going to be the axes of the phase diagrams. All right, so before, I'm going to explain why this phase diagram is, this is the phase diagram of the model. Let me first start off by listing the gap phases. And these are easy to determine analytically by going to the extreme dimerized limits and switching off the layer coupling, the ladder coupling. So we have, in one dimerization limit, we have, with a particular choice of the unit cell, which is this 4-spin unit cell, which is natural for a translation symmetry, explicitly broken Hamiltonian. The Hamiltonian takes support only on these bonds, and the ground state is easily obtained as singlets that live on these bonds. This is a trivial paramagnet, which is a product state. And any kind of vertical coupling, the ZZ coupling, does not really change this. It's stable to small couplings. Now let me go to the opposite dimerization limit, where the Hamiltonian takes full support on the bonds in between unit cells. The ground state is once again easily determined by putting singlets on these lines. And this is a caricature of a symmetry protected topological space. One way to see this is there are, at least in this representation, there are dangling qubits. There's a 4-fold degeneracy on each end coming from 2 spin-a-half. And it's easy to check that small amount of coupling, ZZ coupling, does not eliminate the boundary modes. It lifts the degeneracy from 4-fold to 2-fold, but this 2-fold degeneracy is protected. There are many ways to argue this, but this is the simplest explicit way of checking it physically. So these are the two gap phases. Now the question is what happens for zero dimerization, which I claim corresponds to phase transition. So for zero dimerization, we have two decoupled, at least for no coupling between the ladders, the legs of the ladder, we have two decoupled XXZ chains. And for the choice of the parameters, they belong to the gapless Luttinger liquid phase. So we have a C equal to 2 conformal field theory that labels the transition. Now, the question we have to ask is what happens to this decoupled Luttinger liquids in the presence of interactions? And the best way to do this is bosonize the theory and then study what happens to these perturbations in terms of how relevant they are. So this is easy to do. We can bosonize the decoupled Luttinger liquids in terms of the two XXZ chains in terms of two decoupled Luttinger liquids. For our choice of ferromagnetic coupling, the Luttinger parameter takes values between 1 and 2. The interactions, the vertical interactions, come in the form of 3 operators. There are 2 vertex operators, cosine potentials, and 1 exactly marginal operator. The question of what happens to this C equal to 2 critical theory reduces to whether any of these operators are relevant. So there are standard ways of checking this, and it turns out that at the origin, for no coupling, both the vertex operators are irrelevant. So they don't remove, they don't change the C equal to 2 nature. It continues to be two copies of Lagrange liquids. So there's a small region around the origin where the C equal to 2 nature continues to be stable. But as we increase the value of the rung coupling, the scaling dimensions of these vertex operators are changed. And here's a perturbative result, which we can also measure numerically. We don't need to rely on this. This holds to some extent, but what this tells us is that at some point, for some critical value of the rung coupling, one of the operators becomes relevant and reduces the C equal to 2 theory to C equals 1. So there's a change in the critical theory from something which has central charge 2 to something which has central charge 1. And my claim is that when this happens, the gap phases remains the same. Now that's a non-trivial fact. For example, this is a possibility. Right? It could be that the critical theory changes, but of course that could also mean that the gap phases are also changing. And what we have is a complete ordinary phase diagram. And this is actually easy to check. First of all, we can check this numerically, and this is not true. And it's also easy to check using bosonization by seeing that the bosonized form of the dimerization operator and the bosonized form of the vertical coupling, their energies are minimized by the same field configurations. They're compatible, so they don't frustrate each other. And it's easy to see. Like, when phi 1 and phi 2 becomes pi, 2 pi is also the ground state of the H bulb. Things like that. So the C equal to 2 and C equal to 1 theories are critical segments on the same surface that separates two fixed phases. So what we have is a phase diagram of this kind. And this is a one-dimensional example of what B and Cynthia call multiversality. And if you don't believe the first example, this is a clearer example of how universality class doesn't tell us phases because it's not unique. Yeah, sure. Maybe that was a poor example. Of course, this model is simple. So unlike 3+1 dimensional gauge theories with large number of layers of fermions, this can actually be tested numerically. And here I've shown a simple plot of how the central charge changes as we go with JPERG. And this matches exactly when one of the operators becomes relevant. Before I move on to the next model, let me pause here to see if there are any questions. Or I can also hold out till the end of the talk.
Is there any boundary that extends from the C equals 1 to C equals 2 phase transition? You've got purple region separating the two green lines. Right. The diagram. Yes. The dot, you've got the dot there. Right. Point that goes from C equals 2 to C equals 1. Right. Is that just a point, or are there lines that come out from that?
No. So yeah, I mean, I think this. You mean like this?
The question mark.
Yeah, there isn't. So we can check this numerically, and through bosonization, we can argue that there isn't any line. And the dot, it gives you an impression that there's something special, but no, it's just an ordinary KT transition.
And if I were to go a little bit to the right of this line,
which line?
So you have the vertical line, right. That is your phase transition. But I want to go now into the ordered phase. Right. Now I'm going vertically up.
Right.
Do I sense in any way by, for example, changing critical amplitudes, not so much really critical exponents also, do I sense these transitions from C equals 2 to C equals 1 somehow in the ordered phase?
Well, I mean, the simple answer is that if we have access to long distance correlation functions, yes. But if you're very close to the critical line, depends on how far away we move. But if you have access to long distance correlation functions, we can see that some of them, which were previously algebraically decaying, and we can tell which operators these are now exponentially decaying. So what used to be scaling operators in the C equal to 2 theory are no longer scaling operators. Numerically, of course, they're limited by system sizes, but in principle, yes. All right, so that brings me to the end of the first of the two exotic phase diagrams in quotes. The second example is very similar to the first, in fact, somewhat simpler. One important claim is that this phase diagram we claim is unchanged in the presence of small symmetric perturbations. So we can provide a sufficient collection of symmetries, which if it's preserved, any operators with small coupling constant does not change the nature of this phase diagram. So it's not a fine-tuned phenomenon which requires tuning multiple parameters. So the symmetries that are sufficient to preserve this are an independent U1 spin rotation on each layer and a common spin reflection symmetry, as well as a layer exchange symmetry. So these are, as long as we preserve the symmetries generated by these three generators, spin rotations, spin reflections, and layer exchange, it's easy to see using bosonization that all of these things go through and nothing is going to change. That's right. These symmetries also protect the topology. It also protects this phase diagram. So it protects more than the topological phase. So this is necessary to preserve the phases. If we break too many symmetries, for example, the equal to shrinks to a point. So it involves both the phases and the transition. So as I said, this is sufficient. Maybe there's a way to enumerate the rules of what is sufficient, what is necessary that I haven't figured out. So the second example is a small modification of the first, which is we consider the two copies of XXZ spin chains with alternating bond strengths. And instead of a simple ZZ coupling, we use an XXZ coupling. So we're going to study the phase diagram of this model. Also, one extra detail is that we force the vertical ZZ coupling to be less than 1 in magnitude. And that's the only requirement. Apart from that, we're going to chart the phase diagram with bond alternation and the J-perp coupling. So these are the phase diagram in these two parameters. So I claim that the phase diagram for the model that I wrote down looks like this, the 2D phase diagram. So let me first argue that there exists a single gap phase, no more. And this is easy because there are limits where we can track the phase diagram exactly. So let's start off with one extreme end where the Hamiltonian is completely dimerized and has support on legs that couple unit cells. The ground state is obtained by putting singlets there. And this looks like a symmetry protected topological phase with boundary modes, but these boundary modes are accidental. Any small amount of J-perp eliminates the boundary modes. And in fact, if I take J-perp to infinity, the Hamiltonian takes support on the vertical legs, and the ground state is obtained by putting singlets on these vertical legs. And it's easy to check because it's a 4-spin Hamiltonian that there's absolutely no phase transition. You can just ramp up J to infinity, and we go from singlets that are horizontally aligned to singlets that are vertically aligned, and there's no phase transition. At this point, the Hamiltonian has no parameter, there has no coupling to the dimerization operator. So I can go, So I can go all the way to the other end of dimerization with absolutely no change in the ground state because the Hamiltonian has no dimerization in its parameters. And now I can reduce J-perp and come all the way to the trivial phase when the ground state once again realigns from vertical to horizontal. Now it's a completely product state. So we went from the SPT phase all the way to the right, or what we thought was an SPT phase, and came all the way to the trivial phase without encountering any bulk phase transition. So we can also do this and go all the way back from the lower half plane and then show that this entire phase diagram in the periphery has a single gap phase. Right. So now the question is, what happens to the origin? Once again, with no bond dimerization, we have a C equal to gapless theory. Right? And we want to understand what happens to this gapless theory in the presence of the vertical coupling, the perturbations. Once again, we bosonize this. Once we bosonize it, in the perturbations, there's an extra player in the game. So we had two vertex operators similar to the case before, an exactly marginal operator which changes the scaling dimensions. But now we have a third vertical operator because of the new couplings vertically. So cos theta 1 minus theta 2. Theta and phi are dual variables in the usual way. It turns out that while cos phi 1 minus phi 2 and cos phi 1 plus phi 2 are not relevant, cos theta 1 minus theta 2 is relevant in the standard way that typically is equal to theories are unstable, and this thing gaps it out. So it reduces immediately the C equal to 2 theory to C equals 1, a single component Lagrange liquid. But it turns out that this one is stable until we hit a critical value of the vertical coupling. So there's a stable C equal to 1 line that abruptly terminates to adiabatically connect to the single gap trivial phase. So that's that. Once again, all of this can be verified using bosonization, but also easily verified numerically using DMRG. And I once again shown the plot where we can see the change in the central charge as it goes from 2 to 1 to 0 and connects to the single gap phase. So this phase diagram consists of a stable gapless surface, critical surface, separating a single phase. And this is why I suppose Senthil and B called this unnecessary criticality. This is stable to a less restrictive collection of symmetries, this phase diagram, as long as I preserve spin rotations and spin reflections, which forms an O2 on-site symmetry, as well as a layer exchange. Just these two symmetries are sufficient to guarantee that this phase diagram is stable to small symmetric perturbations. Right. One final thing is the simplicity of this setting gives us access to features that are hard to understand in the complicated field theory setting of Senthil and P, which is we can find out what happens when the universality class changes. Here, it's easy to see that it's an ordinary chaotic transition. In fact, we can also list a sufficient collection of ingredients for phase diagrams of this kind. We need a single relevant operator that gives us the gap phases and a marginal operator that drives the change in the critical surface with some extra ingredients. This can easily be generalized from 2 legs to 2n legs with an appropriate modification of the symmetries. And also we can generate other examples, porting our knowledge from the classification of SPT phases and things like that. So I'll end the talk with a few questions that I don't have an answer to, which is what exactly, how do we construct systematic, what are the necessary ingredients for universality class changing, and whether there are realistic settings where this can be seen. And the big question, which I really have no answer to, is why are such phase diagrams so unusual? Like why is it that it took 2020, like 2019, to come up with examples where such things do happen? That's it. Thank you.
I have a question. Just to roll things off. Do your phase diagrams have a finite temperature analog? Namely, it's in classical stat-mech models.
That's a very good question.
Do you know?
Yes. So there are examples where the 2D classical mechanical models, where indeed the only paper I've seen is by Paul Fendley and Austin Lamacroft and a third author I can't remember, unfortunately, where they have a KT phase transition to an Ising universality class. And this is a purely classical mechanical model, 2D stat mech.
I just make a thought that actually your extra sequels 2 phase in the first one and your unnecessary criticality in the second one are basically from the same origin.
That's right. I agree.
Yes. Like within the bosonization, you have 2 modes within this first phase diagram between a topological insulator symmetry, a trivial insulator symmetry protected phase. Only one of them needs to change. But then the second one just happens to go to 0 as a kind of accident or an unnecessary thing because the operator just isn't there. Some limit delta equals 0. And in the second one, you have exactly the same thing. That operator just isn't there, which is why you get the extra criticality.
That's right.
So it all comes from actually the same origin.
My examples, yes.
In these examples.
Yes.
Okay, but
yeah, I agree. Yeah. It'll be nice to find out if there are other settings also. This is what I could do.
yeah, sure.
Other questions? Okay. Within formal discussion, I think, and let's close today's activities. Thank you very much. I think we will continue tomorrow at 10 o'clock.
These examples, you can sort of say, if you know these 2 phases, you know the criticality between them must be at least this. The central charge will be something, but there might be more by accident.